don't we still fly to distant stars? Well, if not distant, what about close ones? For example, Alpha Centauri, which you are all familiar with. It's the closest star system to us and lies only 4+ light years away. The problem is that what we consider close on a cosmic scale is actually an absolutely unimaginable and so far insurmountable distance for us. The whole lifespan of the modern spaceship's crew members, and even that of hundreds of generations of their descendants, won't be enough to cover this distance. What does humanity need to do to become an interstellar civilization? Or will intergalactic travel remain science fiction? Are we working on interstellar travel technology at all? Or maybe we've already come up with some ideas. Today, you'll learn what types of engines will allow us to fly to the stars and how they work. We'll also slightly lift the veil of secrecy over the warp drive. Is it really too out there? Engines that can reach other stars. To begin with, we need to consider distances to understand the very essence of the problem. Let's take the Moon, for example. It lies 384,400 kilometers away from Earth. That's a lot, but modern rockets deliver devices to the Moon in just 3 days. How long will it take to get to Mars? Here, things are getting worse. In fact, much worse. It takes an average of 9 months to reach Mars. So much for the next planet. But why such a difference? The thing is that the Moon is a satellite. In fact, it's like a huge ISS of natural origin. It also orbits the Earth, so it's very, very close. But the real interplanetary distances are so huge that they're simply beyond our comprehension. This is what the distance from Earth to the Moon looks like. Now let's zoom in. This is the distance to Mars. Keep in mind that we still use kilometers and miles when it comes to our solar system. Whereas, even when talking about the nearest star, we need to adopt a completely different measurement unit. A light year. That is the distance that light travels in 1 year. Let us remind you that the speed of light in a vacuum is about 300,000 kilometers per second. And for all its crazy speed, it would take light more than 4 years to reach the aforementioned Alpha Centauri. We know it's not that easy, but still, try to imagine just how incredibly far that is. In terms of interstellar travel, our conventional rocket engines are not even up to snail speed. They are virtually standing still. To make things clearer, let's look at spaceflight speeds that we can already achieve. 7.91 kilometers per second. It's the minimum horizontal speed an object needs to start orbiting the planet. This is the escape velocity you're probably all familiar with. But it's barely enough to stay in orbit. However, when it comes to flights from Earth to other planets, the minimum escape velocity is 11.2 kilometers per second. Finally, the minimum speed needed to overcome the Sun's gravity and leave the solar system is about 16.65 kilometers per second. It is approximately at this speed that the legendary Voyager 1 flies. As of now, it has been flying for 45 years. It has just left the heliosphere and will reach the Oort cloud only in another 300 years. Have we ever launched something faster than Voyager 1 into space? Yes, but it doesn't change anything. The automatic Parker Solar Probe, launched by NASA to the Sun to study the solar corona, is currently the fastest record holder flying in space. On April 29, 2021, when passing the 8th perihelion, The device reached an unprecedented speed of 532,000 kilometers per hour, or 147 kilometers per second. But how long will it take to fly to Alpha Centauri at such a speed? It's easy to calculate. Almost 9,000 years at the bare minimum. It's a goner. That's why for many decades, every enthusiast, from a science fiction writer to a respectable scientist, has been trying to develop at least a concept of an engine that can help humanity break off the shackles of the solar system. And they've even managed to come up with something. Strictly speaking, no one is stopping you from flying on chemical fuel, as long as it can ensure constant acceleration. The only thing is that due to some intrinsic properties, one needs a monstrous amount of ridiculously efficient fuel. Look at any rocket. This is a giant canister of fuel. By the way, dangerous and extremely unstable. And only at the very top, there's a small capsule with a payload. And all this is needed just to reach our planet's orbit. Obviously, such fuel is not suitable for interstellar flights. But what is a better option? Something that has minimal consumption with maximal yield. And an ion engine seems to be the best fit for this role. Why the best? Because not only are ion engines possible, but they are actually extensively used in space exploration, even though the term itself sounds like it came from a sci-fi movie. The operation principle of such an engine as a whole is simultaneously simple and complex. It involves gas ionization, which is accelerated by an electrostatic field. The result is jet thrust, and accordingly, acceleration of the apparatus. The fuel or working medium of such an engine is an ionized inert gas, most often xenon, but it can also be helium, argon, neon, and others. A mixture of electrons and ions forms in the chamber during engine operation. Without going into complex technical details, let's say that as a result, positively charged particles, ions, are intensively ejected as a jet into space, creating thrust. The advantage of the ion thruster is that the ions on the way out are accelerated to very high speeds of up to 210 kilometers per second. At the same time, chemical rocket engines can't reach a substance ejection velocity of even 10 kilometers per second, staying in the range of 3 to 5 kilometers per second. And yet, the ion engine can work continuously for over 3 years, which by far exceeds the chemical engine's efficiency. Last but not least, it's just beautiful. But there's also a drawback. Currently, technology can achieve only low thrust. Therefore, ion thrusters are used almost exclusively as engines for maneuvering and stability systems. No ion engine could lift the device from the ground. One needs weightlessness to ensure the engine's efficient operation. There's another concept frequently found in science fiction: the photon engine. It may even seem that there's much in common with the ionic one, but in fact, this is still only a hypothetical model. The main idea is to take advantage of the fact that even though photons are massless, they still have energy and momentum. This means that any powerful light creates jet thrust when expelled from the engine. Theoretically, the photon engine could develop the maximum possible thrust for a jet engine in relation to the spacecraft's mass, allowing it to move almost at the speed of light. But the key word here is theoretically. Designing even a photon engine prototype is most likely in the distant future. But there is another interesting concept, which also involves the use of a pulse of light photons, not as a jet, but as some kind of wind. But this time, it's well within our reach, technologically speaking. You guessed it, we are talking about the concept of a solar sail. Surprisingly, scientists are actively working to make this idea a reality. However, so far, we are not talking about sending a fully equipped apparatus somewhere, but only about microchips that weigh close to nothing, which would record the environmental conditions and send data to Earth. Scientists assume that such a sail could be accelerated from the Earth with powerful lasers, and there should be several thousand such chip sails, so that, taking into account potential losses, at least something would fly somewhere. Once again, this is no sci-fi, but a solid research and engineering project with the proud name of Breakthrough Starshot. It even got decent initial funding of $100 million. Now let's digress from the romantic sails, and for the sake of contrast, see what evil human genius came up with in the middle of the last century. From 1958 to 1965, as part of the Orion project, General Atomics, commissioned by the US Air Force, designed some space technology using pulsed nuclear rocket engines. Sounds a little intimidating, doesn't it? But the operation principle is even more unspeakable. The driving force of the apparatus on takeoff should come from nuclear explosions. Charges with a power of about a kiloton should explode at a rate of 1 time per second. Once again, 1 nuclear explosion per second. The shockwave, an expanding plasma cloud, had to be received by a pusher, a powerful metal disc with a heat-shielding coating, and then create jet thrust reflected from it. The impulse received by the pusher plate should then be transmitted to the ship through the structural elements. With the increase in height and speed, the frequency of explosions had to be reduced. Well, of course, it would make all the difference in the world. Yes, back in those years, scientists really worked on this nightmare, but the times were different. In 1965, the project was closed, but only because of different priorities, and by no means because it was considered unpromising or harmful to the planet. On the contrary, according to calculations, one of the mini versions of such a nuclear impulse starship weighing 100,000 tons could reach Alpha Centauri in 130 years, accelerating to a speed of 10,000 kilometers per second. And finally, there's something that quite surprisingly brings science fiction closer to us. In fact, it wills it into solid reality, bringing to mind the legendary Star Trek with its warp engines. Who would have thought that this figment of the scriptwriter's fantasy would suddenly turn out to be not so far from the real laws of physics? To be fair, space warping engines were discussed long before Star Trek. But still, this topic grew into a full-fledged scientific discourse much later. In 1994, theoretical physicist Miguel Alcubierre stirred up the scientific community with an unexpectedly bold solution. He was the first to create a scientific mathematical model within the framework of solving the equations of Einstein's general relativity theory. The model shows that it's theoretically possible to use the curvature of space to move through the universe effectively faster than the speed of light. Ironically, Alcubierre himself is a fan of the Star Trek movie epic and was inspired by it in his search. So, the basic principle of the Alcubierre engine suggests that by stretching the space behind the object and compressing it in front of it, one can achieve the effect of moving at superluminal speeds. Please note, not to move, but to achieve a moving effect, because there are no violations of the laws of physics. It's not the ship itself that moves faster than light, but a certain bubble of space with the ship inside. Strictly speaking, the ship inside the bubble is motionless. This can be compared to a person on an escalator, or even better, a travelator. To get from point A to point B, a person needs to move along the path. But as you can see, they don't even move and still get where they need to. All this time, it's not they who are moving, but the path itself. The same goes for the bubble of Alcubierre, but a section of space acts as a path. As you see, the vernacular term became closely associated with this concept, the Alcubierre warp bubble. One might ask, what's new here? Lots of people thought of all these warps many years ago, and this is what makes the scientist's calculation unique. He presented a comprehensive mathematical model, including how it should work and why, with all the formulas. Of course, this theory has some exotic stuff, to say the least. And it's not even about the gigantic volumes of mass and energy needed for such space curvature, but the fact that these mass and energy must be negative. Yes, this may seem like complete nonsense, but such phenomena don't actually defy the laws of physics. More recently, antimatter was something fantastic, and today we can even obtain it, albeit in tiny quantities. Alcubierre's theory is highly complex and subtle, but nonetheless, it turned out to be convincing enough for other scientists to pick up the idea and significantly improve it. But still, for a long time, due to all these negative masses, Alcubierre's theoretical warp drive remained only a mathematical abstraction. However, the warp